in as much as having a high intracellular ATP concentration would indicate that energy requirements are low. So you can think of like the extreme would be like hibernation, right? You're not more restful than a bear in hibernation. Don't eat for like 3 months. I mean, how is that possible? They just decrease their energy requirements to the greatest extent. Or you can increase the sarcoplasmic and mitochondrial concentrations of ADP, PI, and calcium, which would indicate that energy requirements are high, like going from rest to exercise, or going from mild to high intensity, or high to super high intensity of exercise. So, what does this look like then? If we look at the bioenergetic control of PCR hydrolysis. So think about the time course. At the onset of contraction, we know that we need to have, say, a release of calcium from the sarcoplasmic reticulum to allow for the contraction to occur, right? We showed that in last class. It's one of the steps in generating a muscular contraction. We also know that we have ATP, stored ATP, that breaks down immediately, serves as a buffer at the site of the cell to support an immediate muscular contraction, right? As the other ATP supply systems are being activated. So at the onset of exercise, stored ATP is split into ADP and inorganic phosphate to provide the energy for muscular contraction. So it kind of serves as an ATP buffer. And this immediate increase in sarcoplasmic ADP levels actually turn on creatine kinase. So the phosphocreatine degradation is now dependent on stored ATP breaking down. So the ATP increases intracellular ADP levels, which activates creatine kinase and then serves to facilitate this rephosphorylation of ADP and ATP through the breakdown of phosphocreatine. So stored ATP breakdown is a necessary precursor to actually activate PCR hydrolysis. In addition, the calcium that's released from the sarcoplasmic reticulum is also a signaling molecule indicating that energy requirements have increased, and to activate these rate-limiting enzymes to increase the hydrolysis of phosphocreatine to form ATP and buffer and make sure that ATP its requirements are provided at the level of these contractile proteins. So we have the stored ATP basically signaling through the activation of creatine kinase this energy supply system. So we have a series of steps that are interconnected and reliant on one another, contributing therefore to the sluggishness, right? Is that if you need to follow a series of steps, you can't just go from 0 to 3. You need to follow steps 1 and 2 first in a chain. So we'll take a little bit of time to activate these enzymes, but fortunately there are very fast signaling molecules in that particular regard. If we look at glycolysis then, at the onset of exercise, we now know that sarcoplasmic calcium, inorganic phosphate, and ADP levels are increasing due to stored ATP utilization as well as PCR hydrolysis. Now, these substances will actually increase the rate-limiting enzyme of glycolysis, which is phosphofructokinase, which will then turn on glycolysis. It will increase the rate of glycolytic flux through this enzymatic reaction. So now, glycolysis actually requires the activation of the ATP-PCR system to activate its rate-limiting enzyme. So the turning on of glycolysis depends on the activation of the ATP-PCR pathway. And we know then that glycolysis contributes both directly and indirectly to the rate of supply of the reducing agents for electron transport chain and oxidative phosphorylation. So we need to activate glycolysis to produce NADH and FADH, ultimately to then provide enough energy to turn on oxidative phosphorylation. So you can see step 1, 2, and 3 occurring in some sequence of events. Hence there's a little bit, you can already appreciate that there's some sluggishness in activating oxidative phosphorylation because it relies on the other metabolic pathways to turn on. At the onset of exercise, again, sarcoplasmic increases in calcium, inorganic phosphate, ADP, and NAD. increase due to stored ATP utilization, phosphocreatine hydrolysis, and glycolysis. So now you can see we've got these two energy supply pathways that are being activated, providing these signaling molecules, and these substances will increase the activity of pyruvate dehydrogenase, which we know is that if PDH activity is not high enough, or if pyruvate is being produced at a rate higher than can be converted into acetyl-CoA, it's going to turn into lactate, which is going to accumulate hydrogen ion. So, one of the rate-limiting enzymes of the conversion of basically glucose or muscle glycogen to acetyl-CoA is PDH. So we need to activate that rate-limiting enzyme, and fortunately, these particular molecules, which are activated and increased through the activation of the other energy pathways, do that quite well. These substances, again, activate PDH as well as the activity of Krebs cycle enzymes, including the rate-limiting enzyme that we talked about before, isocitrate dehydrogenase. So it'll make sure that the Krebs cycle and the production of these reducing equivalents will turn on and activate to provide the energy to the electron transport chain as quickly as possible. So therefore, the turning on of the Krebs, I gotta fix this thing. The turning on of the Krebs cycle depends on the activation of the ATP, PCR, and glycolytic pathways. Again, they're not mutually exclusive, they're interconnected. They communicate with one another. So we get to the holy grail of ATP production. It makes sense then that there are a series of signals that would activate oxidative phosphorylation. Again, at the onset of exercise, increases in mitochondrial and sarcoplasmic, again, similar molecules, calcium, inorganic phosphate, and ADP, will increase cytochrome C oxidase and ATP synthase activity, and will turn on oxidative phosphorylation. So we have this interconnectedness of these metabolic pathways that will result in the progressive turning on, the supplying of the reducing agents and energy needed to drive oxidative phosphorylation. So, part of the reason of the sluggishness is that you need these signaling molecules to activate the existing levels of enzymes, which will drive the flux through this mass balance equation of oxidative phosphorylation to create ATP aerobically. Okay? So, in summary, what's causing the metabolic inertia? Under saturating O2 conditions, which is, as you'll see, is under most oxygen conditions of a muscle, except perhaps in extreme hypoxia, it's interesting that the muscle almost always has enough oxygen. We'll get into that later. The substrates of oxygen, the muscle can have more oxygen, but it almost always is above the critical minimal threshold. Doesn't mean that you can't give it more, but it's rarely at some critically low level. But I digress from that. So under saturating O2 conditions, the substrates of oxidative phosphorylation do not increase instantaneously from rest to exercise levels. So you need to increase the number of substrates to drive that enzymatic reaction. It takes a little bit of time for that to happen. The sarcoplasmic and mitochondrial concentrations of these substances or these substrates increase progressively as ATP is broken down and phosphocreatine is degraded. This in turn increases glycolytic flux, which provides the energy and the reducing equivalents as well as other signaling molecules to turn on oxidative phosphorylation by activating these Krebs cycle and mitochondrial enzymes to increase the rate at which ATP is supplied aerobically until ATP supply is primarily being supported by aerobic or oxidative means. Also, contraction-mediated increases in sarcoplasmic and mitochondrial calcium levels, which occur immediately at the onset of contraction, increases the activity of rate-limiting enzymes in both aerobic and anaerobic pathways, therefore turning them on and increasing the flux through these enzymatically driven reactions. So, at any given level of ATP demand, changes in the substrate to product ratio, the number and activity of mitochondrial enzymes, and the amount of intracellular PO2 will ultimately determine the rate at which ATP is produced through oxidative phosphorylation. And ideally, we would like for the majority of ATP produced through this metabolic pathway, in order to optimize our performance, because that's going to delay the rate at which we reach this performance limit. It's going to shallow out that decline in muscle force production and delay the time it takes for the intersection between what the muscle can do and what the task is requiring of it to do. Because when those 2 points intersect, that's when we reach a performance limit. So, I like coming back to the analogy of a car. I use a car a lot. So anybody that has my car, I always somehow come back to a car, to, what is it called, like cruise control. I always come back to a car, aspects related to efficiency, distance, I don't know, it seems like a good thing. It's a good analogy for physiology. So we got the substrates to the products, okay? So let's say that we have this car, and we need to move this car at a particular speed, or a particular rate, say up a shallow grade, okay? So, we have a particular speed. The speed at which this car is going is the external requirements. That's the ATP demand. Okay? But we've got 3 drivers of this ATP demand to produce this particular product. We've got ADP and PI coming from glycolysis and ATP breakdown at the level of the muscle. And also through glycolysis as well. We got intracellular PO2, and we have NADH as the substrates to oxidative phosphorylation. And then ultimately, we've got mitochondrial enzymes that can kind of boost and serve as like high octane fuel to facilitate this. The point here is that imagine your car breaks down, okay? And there's 4 people in the car. So 1 person stays behind the steering wheel and 3 people step out. Now, they say, push this car at 10 kilometers an hour. Okay? So 3 people are behind the car. So now what happens is that if the 3 of us are pushing, if you decide to not push, you and I have to do more work to maintain that speed. Because ATP supply must equal demand. If he's oxygen, and all of a sudden he decides to take 5 minutes off, if we are the other drivers of those products, glycolysis and say ATP, PCR, we have to activate to a higher level to protect ATP because he's slacking. So the amount of oxygen in the cell as a substrate will dictate in large part the relative contributions of the other energy supply systems to make sure that ATP supply is matched to demand. To make sure that the car moves at that particular rate, which is the demand of exercise. This is the one thing that we kind of need to consider in physiology here, particularly in my class. I often talk about constant rates, constant fluxes, constant flows, because it allows you to appreciate when one thing goes up, another thing can go down. To maintain this constant, if he slacks, what do we have to do? If he increases his contribution, we can take a day off. But it's key to say, to achieve this goal, what happens to the mechanisms underlying that goal? So again, you'll see that emerge throughout the class when we talk, and in exercise pathway, we talk about kind of like constant rate exercise or fixed demands, because I think they're important in terms of understanding human physiology. So this is just a very simple, and hopefully I've tried to demonstrate already that these energy supply systems do not operate in isolation. They're interconnected and they communicate with one another. Okay? So, for example, if your intracellular PO2 is 0, you're not accepting any of those. There's no oxygen to accept the electrons and the hydrogen ion, and so in this case, all of the ATP would need to be provided through non-oxidative means. But even when there's tons of oxygen in the cell, the majority of ATP is going to be provided by oxidative phosphorylation, and there's still going to be a contribution from the energy pathways, because those energy pathways are required to signal to oxidative phosphorylation to keep going. So it's not like it's an all or not phenomenon. They're all contributing, but the relative contributions will be determined by the various factors. So like say for the amount of oxygen in the cell. If oxygen levels go up, you can have a lesser reliance on the other metabolic pathways to produce and match ATP supply per minute. So these are not mutually exclusive. They're occurring all together and they're all contributing to ATP production. So, I know we have a couple more minutes, but I would like to get through this because I think this hopefully ties it all together. So here we have the control of bioenergetics, particularly focusing heavily on oxidative phosphorylation here. So, we know that, so we've got the three major substrates, so ADP, PI, NADH, and intracellular PO2. In the presence of mitochondrial enzymes, will produce ATP. That ATP drives force. So in this particular, let's again consider performing exercise at a constant load equivalent to 50% of your peak power output, which would be a constant VO2 or a constant ATP demand. Okay? So if we have an increase in ADP and PI, this would be, as we showed, a signal for activation of glycolysis to try to protect or match ATP supply and demand. We said that increases in hydrogen ion can contribute to muscle fatigue development and loss of force production by inhibiting the release of calcium from the sarcoplasmic reticulum. So that can decrease, that can compromise muscle force production. And by competing with calcium binding sites on troponin. And this will ultimately decrease myofibril calcium sensitivity. So the idea is that the more hydrogen ion there is, the less muscle force can be produced. So we'd like to keep hydrogen ion levels in the cell low. Importantly, if we have disturbances in inorganic phosphate, increases in intracellular inorganic phosphate levels, they have dramatic effects on muscle force production through various pathways. They inhibit actin-myosin cross-bridging, no cross-bridging, no force production. They decrease myofibril calcium sensitivity. So the myofibrils basically don't bind to calcium as well, so they don't produce force as a result. Decreasing binding of calcium to troponin C, and ultimately and most importantly, increases in inorganic phosphate serve as a signal to inhibit the release of calcium from the sarcoplasmic reticulum. So any one or combination of these factors mediated by an accumulation of inorganic phosphate in the cell will contribute to a faster rate of decline in muscle force production. And therefore, muscle will be unable to produce the force required for the task earlier in time. So again, this is like the person playing video games in their mom's basement versus being a millionaire through endorsements because they can complete a cycle of the Tour de France more quickly. Okay? So, in the last couple minutes that we have, and then we'll start next class with some examples to try to anchor all of this together conceptually. So, let's say for example that we're exercising, we have a constant force output, a constant force. So, let's say for example that I have a maximum force of, say, 100 newtons, and so now I'm trying to generate contractions at 50% of that. The idea is that I have a constant contraction frequency, a constant ATP demand, and therefore a constant VO2 demand. Okay? So, at a constant load exercise of, say, 50% of your peak capacity, i.e. at a constant ATP demand, if I decrease intracellular PO2 levels, so he stopped pushing the car. How can we maintain ATP at the level of the cell to support this force requirement when he slacked off? We can activate glycolysis. We can buffer the ATP supplies by decreasing stored ATP, by increasing phosphocreatine degradation. But the implications for fatigue is that when there's a decrease in intracellular oxygen levels to support a given rate of ATP supply, you will have an activation of glycolysis, an accumulation of hydrogen ion, accumulation of inorganic phosphate, which through the mechanisms that I showed you on the previous slide will increase or speed up the time at which your muscles will fatigue and stop being able to produce the necessary amount of force. So let's come back to this. I don't show these things for no reason. Try to come back conceptually. To perform a given amount of exercise, 50% of your peak power output, is that if you have low intracellular PO2 levels, remember, the slope of this dotted line reflects the rate of muscle fatigue development. So the more vertical it is, the worse it is. So when you have low intracellular PO2, because you have to activate these other energy supply systems to make sure that 50% of your peak power is supported by a given amount of ATP, when it's not being driven by oxidative phosphorylation, it needs to be driven by the other metabolic pathways. That comes at the expense of a more rapid deterioration in muscle force producing ability, and therefore you reach your performance limit earlier. If you can have higher intracellular PO2 levels, you can delay that rate of deterioration and the time it takes for you to reach that performance limit. The opposite is true. Same ATP requirement, same force production. Now all of a sudden, we increase the number of capillaries. We start sucking in on, say, oxygen, whatever it is. We increase oxygen transport mechanisms, which we'll talk about. Now, this is like him as oxygen pushing harder. The car still needs to go 10 kilometers an hour. So if he's now contributing 75%, we only have to contribute 25% collectively between the two of us. So to move the car at the same rate, we can take a day off. So we don't have to activate and accumulate these metabolites to the same extent to signal the activation of oxidative phosphorylation to drive through that enzymatic reaction. Because we increase the substrate, we can get away to have the same flux through the reaction with lower of the other substrates. The implications of fatigue then is that we actually have a signal for decreasing the rate of glycolytic flux. We have less accumulation of hydrogen ion and inorganic phosphate, and therefore we can exercise longer at a given power output or a given ATP demand. Now what happens finally, at a given force production, a given ATP demand, if we increase the number of mitochondrial enzymes, but we did nothing to, say, intracellular PO2 levels. Again, we could get away with a lesser reliance on glycolysis and ATP breakdown and phosphocreatine hydrolysis because we can drive oxidative phosphorylation at the same rate with more enzymes and less substrate. So the implications of fatigue then is that we get less signaling glycolysis, less accumulation of hydrogen ion and organic phosphate, and when we have high enzymes, which means high mitochondrial density in a given muscle cross-sectional area, we can exercise longer because we accumulate these fatigue-causing metabolites at a slower rate. So we'll get into this, we'll use this as a review, these next slides as a review at the start of next class. We'll try to anchor the integratedness of it all. Alright, see you on Thursday morning. And for those of you that have lab on Thursday, enjoy.